So let me start with something that seems simple. You're sitting in a train, right? And you throw a ball forward at 10 miles an hour while the train is moving at 50 miles an hour. How fast is the ball going? Well, from outside the train, someone sees it going 60 miles an hour. Simple addition, 50 plus 10. This is what Galileo told us, what Newton told us, and it works perfectly for everything we experience in daily life. But then, in the late 1800s, people started doing experiments with light. They measured the speed of light very carefully. And here's where things get weird. They found that light always travels at the same speed. Always. It doesn't matter if you're moving toward it or away from it. It doesn't matter if the source is moving. Light always goes at about 186,000 miles per second in empty space. Now wait a minute. That can't be right, can it? If I'm on a train moving at, say, half the speed of light, and I turn on a flashlight pointing forward, shouldn't the light from that flashlight be going at the speed of light plus the speed of the train? But no, experiments showed that's not what happens. The light still goes at exactly the same speed someone standing still would measure. This drove physicists crazy. How could this possibly be true? And you know what the young Einstein said? He said, what if this is just how the universe works? What if the speed of light being constant is more fundamental than our ideas about space and time? Now, I want you to really think about what this means. If light always travels at the same speed, no matter how you're moving, then something else has to give. And what gives is our common sense notions of space and time. Let me give you an example. Imagine you have a clock made of light. It's simple. A light beam bounces up and down between two mirrors. Each time it bounces, that's one tick. Now, if this clock is sitting still, the light just goes straight up and down. But if the clock is moving past you, from your point of view, the light has to travel a diagonal path because the whole clock is moving sideways while the light bounces up and down. The diagonal path is longer than the straight up and down path, but the speed of light has to be the same. So the only way this works is if time itself runs slower for the moving clock. It's not an illusion. It's not a trick. Time actually runs slower when you're moving. And you might say, come on, that's ridiculous. But it's been measured. We've got particles called muons that rain down from the upper atmosphere. These things decay in about 2/millionths of a second. At the speed they're moving, even going nearly the speed of light. They shouldn't be able to reach the ground before they decay, but they do reach the ground. Why? Because from our point of view, their clocks are running slow. They're experiencing less time than we are. Now here's where it gets really interesting. If time slows down when you move faster, what happens to your mass and energy? Let's think about pushing something. When you push an object, you give it energy and it speeds up. In normal everyday experience, if you keep pushing with the same force, you keep adding the same amount of speed. But remember, as things go faster, time runs differently for them. Suppose you've got a particle and you're accelerating it faster and faster. As it gets closer to the speed of light, something remarkable happens. It gets harder and harder to speed it up more. It's like the particle is getting heavier. In fact, we can describe it exactly that way. The effective mass of the particle increases as it goes faster. And here's the key. As you approach the speed of light, this effective mass approaches infinity. Let me say that again, infinity. Now think about what this means. To accelerate something, you need force. And force is mass times acceleration. If the mass becomes infinite, you'd need infinite force, infinite energy to push it any faster. You can keep putting energy in, more and more energy, but you can't quite get to the speed of light. It's like climbing a hill that gets steeper and steeper the higher you go, until at the very top it becomes a vertical wall that goes on forever. You can keep climbing, getting closer and closer, but you can never quite reach the top. We see this in particle accelerators all the time. At CELAC, we accelerate electrons to more than 99.9999% of the speed of light. We pump enormous amounts of energy into them, but they never quite reach light speed. The energy just keeps making them act like they have more and more mass. Now, why is it that light can travel at this speed? Well, here's something beautiful. Particles like photons that make up light have no rest mass. Zero. None. If you could somehow catch a photon and weigh it when it's sitting still, well, you can't because it's never sitting still. A photon is always moving at the speed of light. It can never be at rest. And because it has no rest mass, it doesn't have this problem of mass increasing as it speeds up. In fact, for a massless particle, The only speed it can travel at is the speed of light, not slower, not faster, exactly at that speed. So the universe has this speed limit built into its very fabric. It's not that light speed is the limit because light is special. Light goes at this speed because light is massless. And the speed limit is this fundamental property of space and time themselves. Let me tell you what this really means. See, we used to think space and time were like a stage where physics happens. Fixed, absolute, the same for everyone. But Einstein showed us that's wrong. Space and time are flexible. They bend and stretch depending on how you're moving. There's this thing called space-time, where space and time are woven together. When you move through space, you're also moving through time. And there's a maximum rate at which you can move through this combined space-time. That maximum rate is what we call the speed of light. It's like this. Imagine you're walking, and you can walk at a certain maximum speed. If you walk straight north, you're using all your speed going north. But if you walk northeast, part of your speed is going north and part is going east. So you're not going as fast in the north direction. In space-time, everyone is always moving at the speed of light through space-time. Always. When you're sitting still in space, all your motion is through time. You're aging at the maximum rate. But when you start moving through space, some of that motion through space-time gets diverted into motion through space, which means you move slower through time. You age more slowly. And if you could somehow move through space at the speed of light, all your motion through space-time would be motion through space and none through time. Time would stop for you completely. You wouldn't age at all. But remember, you can't actually get there if you have mass. The closer you get, the more energy it takes, approaching infinite energy. So the speed of light isn't just a speed limit for moving through space. It's the conversion rate between space and time. It's the fundamental speed limit of causality itself. It's how fast cause and effect can propagate through the universe. Now here's something that really bakes your noodle. If you could go faster than light, you could arrive somewhere before you left. You could create paradoxes. You could violate causality. The equations of relativity tell us that if faster than light travel were possible, it would be the same as traveling backward in time. And that's not just weird, it's logically impossible. If you could send a signal faster than light, I could send you a message before you sent me one. I could tell you not to send the message. Then you wouldn't send it. Then I wouldn't know to tell you not to send it. Then you would send it. See the problem? So the speed of light, being the cosmic speed limit, isn't some arbitrary rule that nature decided on. It's a consequence of the way space and time are connected. It's about the very structure of reality. You know what I find amazing? This whole thing came from taking seriously the experimental fact that light speed is always the same. Einstein didn't just explain that fact. He followed it to its logical conclusions and discovered that space and time themselves must work differently than we thought. The equations are actually quite simple. The relationship between energy, mass, and momentum is given by E squared equals P squared C squared plus M squared C to the fourth, where E is energy, P is momentum, M is rest mass, and C is the speed of light. For a particle at rest, momentum is 0, and you get E equals mc squared, that famous equation. It tells you how much energy is locked up in mass itself. For a particle with no rest mass, like a photon, the mass term is 0, and you get E equals pc. Energy equals momentum times the speed of light. And if you work out what happens as a massive particle goes faster and faster, you find its energy keeps growing. At very high speeds, most of the energy is in the motion, not in the rest mass. And as velocity approaches c, the energy approaches infinity. You can pump infinite energy in, and you'll never quite reach light speed. It's built into the mathematics of space-time. The Lorentz transformation, which tells you how to translate between different reference frames, has this factor: 1 over the square root of 1 minus v squared over c squared. As v approaches c, this factor goes to infinity. This shows up everywhere. In time dilation, in length contraction, in mass increase. It's all the same thing, the geometry of space-time. And we've tested this, not just with particle accelerators. GPS satellites have to account for relativity, or your navigation would be off by miles. We've flown atomic clocks around the world and compared them. We've measured the lifetimes of fast-moving particles. Every single test confirms Einstein was right. So why is light speed the limit? Because space-time has a structure, and that structure has a maximum speed built into it. It's the speed at which massless particles must travel, and the speed that massive particles can approach but never reach. It's the speed of causality, the maximum rate at which information can propagate. It's not that we haven't found a way to go faster yet. It's that the universe fundamentally doesn't allow it. Going faster than light would be like making a triangle whose angles add up to more than 180 degrees in flat space. It's not just hard, it's logically inconsistent with the geometry of the space you're in. And once you understand this, you see that light speed isn't really about light at all. Light just happens to travel at this speed because photons have no mass. The real speed limit is about the fabric of space and time, about how the universe is put together at its most fundamental level. That's what Feynman would tell you about light speed. It's not a barrier we're trying to break, it's a window into the deep structure of reality itself. And understanding why we can't break it teaches us far more about the universe than breaking it ever could.